students, you've made it to week number 2 of online learning. Hopefully you're like me and your eyes have not burned themselves out by staring at the screen too much. Today we're going to be talking about something called phylogenics and phylogenies. Phylogenetic trees. Phylogenetic trees. That's what we're going to be talking about today. To help me explain this concept, I'm going to turn to the distinguished family of limb. We will be looking at several different species in this family, and then we will be discussing them through a phylogenetic tree.
Here we have the Anikis, and here we have the Dadicus. Here we have the Mamacus. This is Dadicus limb. Dadicus limb has features such as a flat nose, long arms, and short hair. This is Mamacus limb. Mamacus limb has a very distinguished nose, short arms, and short hair. This is Anikis limb. Anikis limb has features such as a flat nose, short arms, and short hair. This is Rubicus limb. Rubicus limb has a flat nose, long arms, and long hair.
It's notebook time!
So, we are now on page 110. Our topic for today is phylogenetics, or phylogenetic trees. We probably want to get a definition for what phylogeny and phylogenetic trees are. Let's start off with phylogeny. Phylogeny, to put it simply, is going to be the study of evolutionary relationships between different biological species. And biologists who specialize in phylogeny are often going to use special tools called phylogenetic trees. Phylogenetic trees are going to be the diagrams that actually kind of resemble trees in some way. I'll show you guys in a second. Now, it is easiest to show you guys what a phylogenetic tree is by going through an example. We're going to use the example of the limbs and the different species of limbs. I'm going to show you a second example, so what I would recommend doing is to split up the rest of your page for 2 examples. Example 1 is going to be with the limb family. I'm switching to a longer piece of paper for clarity, but I would suggest you continue with your notebook if you'd like to capture these notes. After meeting all of these wonderful limbs, we can start to record some data about their different physical traits. This will tell us the relatedness of the limbs and their species. For example, if you were watching closely, you would have noticed that the only species of limb with a distinguished nose and not a flat nose was the Mamacus. For long arms, Dadicus and Rubicus possessed long arms, whereas Mamacus and Anikis were more petite with the shorter arms. And finally, there is only one limb with long hair at the moment, and that would be the Rubicus. I have a table set up here with my different traits. Now, using this table that has different physical traits, I can compare which species are maybe more closely related to each other and which ones kind of diverged from the others at some point. You'll notice up here that I have drawn a Y-shaped curve. Why? Great question, Rubicus limb. That's because I'm talking about having an original population of limbs that began to diverge from each other into different species, most likely through disruptive selection. I noticed that all of my species of limbs have a flat nose except for the Mamacus. This highly suggests that Mamacus went off and kind of evolved on her own. Perhaps she lived in an environment where she needed that heightened sense of smell, and therefore she does not possess the flat nose of the others. To symbolize this, I'm going to pretend that this is the starting point of my diagram. I'm going to call it the root. And I'm going to say that if I follow from the root up to my species, I'm going to see that this is Myrmecus. However, if I follow the root up towards my other species, I'm going to notice that they must pass the flat nose marker, so at some point they acquired the flat nose trait, which means that all species past this marker have a flat nose. Having looked at the flat nose trait, I'm going to move on to the long arms trait. I notice that two of the limb species, the Deticus and the Rubicus, have longer arms, whereas Myrmecus and Anikis don't. This suggests to me that once again we had a divergence of species, some disruptive selection, and all species beyond this point had long arms, whereas some species decided to evolve to a point where they did not need long arms. This implies that Anikis is our next species to diverge from the rest of the population. Again, meaning if I go from the root of my diagram, I can see that Anikis does have a flat nose. She passes that point, but she does not have long arms, so therefore she must have flat nose and short arms. Leads me to my last two species and the last trait, long hair, Deticus versus Rubicus. Once again, one of the species branches off at some point without long hair. That would be Deticus. Whereas Rubicus is the final species to evolve. I'm not surprised. Who has long hair? That is the basics of a phylogenetic tree. You can tell it does look like a tree because it's got a root, origin, and then branches, basically points where species diverged off from each other. You'll also notice that it includes small markers for traits. So all of these things, flat nose, long hair, long arms, are going to be considered traits. Distinguishing traits that help us differentiate between the species. On the other hand, on the top of your phylogenetic tree, you've got all of your current species. Often scientists use these to compare species. Sometimes they use them to compare between families or kingdoms of animals. So often these are just going to be called taxa, basically groups of animals that they want to compare. 2 more points about the phylogenetic tree. If I asked you where you could find a common ancestor for Myrmecus and Anikis, could you do it? Well, the answer lies in the intersection point of our diagrams. So if I trace back Myrmecus's timeline and I trace back Anikis's timeline towards the root until they actually merge, this portion is going to be called a node. And this particular node is going to signify a common ancestor. In fact, it signifies the common ancestor of all the species. Because if I look at it, Myrmecus, Anikis, Deticus, and Rubicus can all trace back to this one single point. This would be an additional node, but this node is the common ancestor of Anikis, Deticus, and Rubicus. And then our final node is going to signify the common ancestor of just Deticus and Rubicus. Finally, phylogenetic trees are special because they don't just follow these line diagrams. The length of the lines signify something. The length of the lines is going to signal time. And when you're talking on the evolutionary scale, how species actually diverge from each other, you could be talking eons. These trees are actually extremely helpful for evolutionary biologists because they can also track when species went extinct and when common ancestors could potentially be found. For example, let's add one last branch to the limb phylogenetic tree. Limb phylogenetic tree right here is going to have Star, the baby Easter chick. The story behind Star is that he was technically Anna's, but then I got sick one day when Anna was out, so Anna forgot to feed them. I forgot to feed them. I blamed Anna, Anna blamed me. Basically, Star died. Sorry, I don't know if I was clear. Star was a baby chick we were trying to raise for Easter. This was probably when we were about 7. 8. Please don't blame me too much. I know there is slight irony in the fact that I'm now a biology teacher and teach about life, and I killed a baby chick before Easter. Wait, no, Anna killed the baby chick before Easter, I'm pretty sure. I think the trait for Star versus Momicus, Anicus, Daticus, and Rebecacus is quite easy. It's probably just the fact that they are human, whereas Star was a beautiful chicken. What you might notice, though, is I drew Star's branch so that it stops rather abruptly in time. If this was the ancient past and this is the current present, and time is going in the upwards direction, I'm going to notice that, yeah, Star survives for some time, but he ain't alive in the present. Let's have a moment of silence for Star. That's pretty much the idea behind phylogenetic trees, guys. By just looking at the diagram and how I labeled it, you should get a good idea of how they function. They show divergence of species from each other based on physical traits. They also show how they've evolved over time, or at what points in time they've evolved, and where you might potentially be able to locate a common ancestor. If you would like one more example, I'm going to do one more example using some random leaves I found while walking around my neighborhood. But if you're feeling good, you could probably just move on. Of course, if the practice gives you some difficulty, feel free to come back later and look at the second example as well. In this example, I'm going to be discussing some really beautiful green leaves that I found from different trees around our house. While they all are beautiful and green, they definitely come from different types of trees. So let's see if we can use a phylogenetic tree to kind of classify what are these different trees and maybe which ones are most related to each other. First of all, I can see that there's 2 distinct categories of leaves if I start to look at all 5. I've got ones that have these tooths, I'm going to call them. These tooths are going to be just like our teeth. They have kind of a sharp pointed edge, whereas these have a slightly more rounded feel. So let's see, these 2 I'm going to probably categorize into teeth. This guy has some pretty sharp teeth as well. Don't know why I was saying tooths earlier. It's okay, guys. You understand, I hope. This one I'm going to say has no teeth and is quite rounded, even though it's a little bit pointy at the end. So we've got 2 categories of leaves already to start with. I don't even know all the species of these trees, but I'm going to quickly identify them so you know what's going on. All I know is that all of these guys are some type of oak. So I'm going to call this oak 1. This one was oak 2. He's a lot skinnier. And this guy is unknown species unknown. Just found him growing in a piece of dirt. Over here we've got a crepe myrtle tree. Beautiful pink flowers in the spring. And then over here we've got a holly tree, which has lovely, lovely red berries when it gets a little bit colder. I've already divided these trees into, or these leaves, excuse me, into 2 categories. I have ones that have teeth and ones that have no teeth. If I want to, I can look further into each category and further differentiate these species based on some physical characteristics. Let's do it. So the first thing I noticed about the crepe myrtle and the holly versus their size is that the holly has this shine to it, which means it's kind of a waxy leaf, whereas the crepe myrtle has no shine or very small shine compared to it, and it feels a lot more velvety compared to like that smooth wax. So I'm going to say holly has wax or a waxy finish. This helps make it water repellent and not have the leaves mold as much because the water will roll right off it. And crepe myrtle is not very waxy. So if I'm comparing these 2, I'm going to notice quite a few differences between these 2 species. However, the one key difference that I'm going to focus on for today is going to be their texture. Once again, oak number 2 has got a smooth, almost waxy finish, kind of like the holly. Whereas this unknown species has a very strange, fuzzy sort of feel. It's almost like rubbing your hand on Velcro. So I'm going to label those as being my two characteristics. We've got fuzzy and we've got not fuzzy. Remember, labeling your characteristics in terms of positive and negative is actually quite helpful when you go in to make your phylogenetic tree. And it's finally time to make our tree. You might notice that I categorize these a little bit strangely. So I have 3 species that had teeth, and then I further broke them down. And then I also had 2 species that had no teeth that I further broke down. So when I'm making my tree, I actually want to keep this in my diagram. What that's going to end up looking like, and bear with me, is going to be 2 separate groups in my diagram. You might be asking, Miss Lim, why are you suddenly doing these weird straight lines instead of the beautiful V shape that we saw for the phylogenetic tree earlier? I'm doing this just because if any of you guys move on to study organization or organizational sciences, they'll use both of these different diagrams depending on what they're comparing. They generally mean the same thing, though this one does not indicate time as clearly as the phylogenetic tree. So I'm going to call this one instead a cladogram, and you'll see in a second why. Also get used to, like, this is still the root of the diagram, and this time we're going to be traveling this direction from left to right instead of up to down like we were doing with the phylogenetic tree earlier. But anyway, we had 2 different groups. We had the group with teeth, and we had the group with no teeth. Smooth. Okay. Within the with teeth group, or within the no teeth group, I then had 2 species that actually fit here. I had the crepe myrtle and I had the holly. My distinguishing characteristics between them was that they're either not waxy or waxy. So I would add my tick mark for waxy here and add my tick mark for not waxy here. Let's make sure this holds true. So starting from the origin, the leaf has no teeth. It is also waxy. Must be a holly tree. Let's double check. Holly tree, yes, is no teeth and waxy. Once again, root of the diagram has no teeth, is not waxy, must be a crepe myrtle. You can see how these diagrams are very useful for organizing information in general, not necessarily related to evolution. We're now going to go into the other ones, the ones with teeth. If I remember, I had 3 here. So let's take a look at their characteristics. I had characterized them based on being not round or round, and then fuzzy or not fuzzy. The main differentiating characteristic for the first round would be round versus not round. Sorry, that was an unintentional pun. And so that's going to leave oak number 1 by himself, because oak number 1 was not round, whereas my other 2 are round. In this type of cladogram, when I'm moving left to right and I'm having these weird football-shaped goals, I'm going to add another series like this. It's like adding another branch to your tree. And I'm going to compare my last 2 species question mark and oak number 2. In this case, it doesn't really matter where I put them because they're my last species. Species question mark and oak number 2. And I'm going to make sure that I add in my traits as necessary. So species question mark was round and fuzzy, which distinguished him from oak number 2, which was not fuzzy. Let's double check really quickly. So going from the root, we're going to see that if the leaf has teeth, if the leaf is round, and if the leaf is fuzzy, it's going to be species question mark. And that sounds appropriate. You can barely see down here. He does have teeth. Let's take a quick look at this cladogram, and I want to point out just a couple things. Cladograms usually don't show time, they just show organization. And when they have these sort of species that are kind of side by side, as in the crepe myrtle and the holly, or the species question mark in the oak, that generally implies that there's not enough of a difference between these two species to really know which one diverged first or which one evolved last or first. The name for species like this that are grouped together, and it's unclear which ones evolved first, is going to be a sister group. Aww, sisters. And because it's biology and they just love throwing around terms, it's a sister group. It's also sometimes called a clade. And that's where you get the name cladogram, because it's got that clade in there, cladogram, clade, from the pairing of species that are very similar, and that it is difficult to tell which one came evolutionarily first.
It's now your turn. I want you to find 5 objects in your house, or organisms if you have some living things around you, and I want you to draw and design your own phylogenetic tree that holds true for traits among those 5 organisms. For more information, you should look at the assignment on Google Classroom.